Okay, so I am now live streaming to YouTube. For those of you on YouTube, you will be hearing this a bit later than the rest of us who are on the network. And we will start in just a little while. I think we have half a minute or so, just to see if we have more people arriving. Okay, I think we have a few people now. I think I'll start anyway so that we can get to the important bits. So thank you everybody for being here. I'm Sheila Heymans and I'll be your moderator today. Welcome to the Ecopath online seminar series. Just for those of you who don't know me, my name is Sheila Heymans and I'm the Executive Director of the European Marine Board, and we are hosting this webinar on our YouTube channel for now. Just some housekeeping rules. Please make sure that your name is clearly entered when you come in so that we know who's asking questions. Please make sure that you use the Q&A, which is at the bottom of your screen, to ask questions, and make sure that your name and where you're from is in there. And then when the questions, when the speakers finish, then I'll read some of these questions out for him. If you have any technical problems, then please use the chat and deal with them. Please note that the webinar is being recorded and it's available on YouTube, at first on the Marine Board, but then it'll also be the Ecopath YouTube channel. And I think I'm hearing some noise in the background, so just mute people there. Okay, so it is a series that the Ecopath series is held every 2 months on usually the last Tuesday of the month at 12 noon Eastern time, and 6 o'clock Brussels time. It's not the last Tuesday of the month because I couldn't do it next Tuesday, so we're having it today. So today is happening, and then the next one will be on the 25th of January. And our speaker today is Quentin Nogues. Sorry, I'm really not doing well with your last name. Who's from the Berea lab in Normandy. And he is a PhD student who tells us he's going to be defending his PhD on the 2nd of December. So we should ask him very difficult questions today. And his title for the talk today is Ecospace and Ecological Network Analysis, a holistic approach to assess the spatialized cumulative effects of multiple anthropogenic drivers on ecosystem functioning. So without further ado, I will stop sharing and I will stop sharing. And Quentin, you can start sharing and go for it. Yes?
Yes, that's it. I'm starting with the share right now. So hello everyone, thanks for coming. So today I'm gonna present you part of the work that I have been doing during my PhD in this presentation entitled Ecospace and Ecological Network Analysis, a holistic approach to assess the spatialized cumulative effect of multiple anthropogenic drivers on the ecosystem functioning. So with 50% of all humans living near the coastline, coastal and marine ecosystem plays a key role for human societies. They provide highly valuable ecosystem services and house a large diversity of marine species. Unfortunately, these ecosystems are threatened by the ever-growing number of human activities. Indeed, with the overexploitation of terrestrial ecosystems, humans are increasingly looking to the sea. We can take, for example, the Bay of Seine in the English Channel, one of the most anthropized systems in the world. With its important marine renewable perspectives, multiple offshore wind farms are under consideration, and one is under construction, the offshore wind farm of Courseulles-sur-Mer, located right here in the Bay of Seine. The multiplication of anthropogenic drivers can lead to hard to predict effects called cumulative effects. They are the result of the interaction of the multiple ecosystem changes caused by anthropogenic drivers and can have dire consequences for the ecosystem functioning. One way to understand the effect of anthropogenic drivers on the ecosystem is to look at food web model. They model the predator-prey relationships and gives us clues on the direct and indirect effects of anthropogenic drivers on the ecosystem. For example, offshore wind turbine can increase the biomass of bivalvia by adding new hard substrate to the environment. This can have direct effects on the prey of the bivalvia as well as on the predator of the bivalve, but also indirect effects on other group of the food web. However, it can be hard to fully comprehend the effect of a driver on the ecosystem functioning because food web models can be highly complex and can give us a high amount of information. That is why ENA indices were built. There are indices that gives us key information on the whole ecosystem functioning, organization, and structure. There is a wide range of ENA indices. They are called the holistic indices because they look at the entire ecosystem functioning. And they reach, for example, the very well-known mean trophic level, which look at the overall structure of the food web. But there is also lesser known indices like the fin cycling index, which look at the overall recycling in the food web. The system omnivory index look at the overall omnivory of the food web, which is how groups are going to eat at different trophic level. There is also the detritivory on herbivory, which look at the sources of energy for the food web. And finally, there is more complex indices like the relative flow redundancy, which look at the relative redundancy of the trophic pathways in the food web. All of these ENA indices gives us information on the functional properties of the food web, which can be linked with ecological theories to emerging properties such as the ecological resilience or resilience of the ecosystem. The ecological resilience or resilience of the ecosystem is the ability of an ecosystem to resist to perturbation through self-reorganization and through its reserve. So the objective of my work was to study the effect of anthropogenic drivers on the ecosystem functioning and ecosystem resilience. And to do so, I've divided this presentation in 3 parts. So first, I will describe the food web model that I used and how I modeled multiple anthropogenic drivers. Secondly, I will show how the food web model function changes due to the different anthropogenic drivers. And lastly, I will look at the potential cumulative effects resulting from the interaction of the different anthropogenic drivers and how this will impact the ecosystem functioning and its resilience. So the model that I used for my work was the extended Bay of Seine Ecospace model. This model simulates the food web of the extended Bay of Seine and was built by Halwani et al. In 2020. The extended Bay of Seine is located between the French coastline and the easy delimitation between France and the United Kingdom in the Eastern English Channel. It was first built to test the reserve effect of the future offshore wind farm of Courseulles-sur-Mer, here located on the map in yellow. It was built from an Ecopath model, which was composed of 42 groups, including 40 living groups going from marine mammals to bacteria and 2 non-living ones. It was then later used to build an Ecosea model, the Ecosea model of the extended Bay of Seine, which was set to run from 2000 to 2015, using 29 annual time series. Finally, the Ecospace model of the extended Bay of Seine was built with 4,907 cells, each modeling a ecosystem time dynamic food web model. And the group distribution was driven with an habitat map, a depth map, and a primary production map. As said earlier, the model was first built to test the reserve effect of the offshore wind farm. But in order to do a cumulative effect assessment, I needed to model different anthropogenic drivers and a multitude of them. So I decided to focus my work on the reserve and the reef effect of the offshore wind farm of Courseulles-sur-Mer, on the effect of climate change on species distribution and species dynamic, and on the effect of fishing using multiple fishing scenarios that I will describe later. To model these new anthropogenic drivers, the habitat map used to drive group distribution and group dynamic in the Ecospace model was replaced by environmental drivers maps. To put it simply, Along with biotic interactions, environmental drivers maps allow us to define suitable and unsuitable habitat based on group preferences. Based on the foraging arena theory, the more suitable an habitat is for a set group, the more the set group is going to consume, and thus is going to produce. The suitability of an habitat can be defined by multiple environmental drivers associated to response curve. In the extended Bayesian ecospace model, we computed environmental driver maps using species distribution model. Species distribution model are correlative approaches which use environmental parameters and species occurrences in order to determine the theoretical niches of species. This allows us to know the species preferences based on their current and past distribution through suitability index map. We used several environmental parameters in our species distribution model, including various temperature map at different depths, a sediment type map, a slope map, and a northerness map. We used suitability index map created with species distribution models as the environmental driver for 27 of the 40 living group of the extended Bayesian ecospace model. The advantage of the species distribution model is that they can also be used to extrapolate the effect of changing environmental parameters on the suitability index. This can be used to estimate the effect of climate change on the species bioclimatic niches, and thus can inform us on the effect of climate change on the species of the extended Bayesian. To simulate the effect of climate change, we forced our species distribution model with the IPCC RCP 8.5 forcing scenario at two different type steps in 2050 and 2100 in order to create new suitability index maps taking into account the effect of climate change. We then introduced this new suitability index map in the Ecospace model using the spatial temporal framework of IWI in order to model the effect of climate change on the group suitability compared to the reference suitability index. We then let the model run for several years until biomasses were stable as it is needed to compute ENA indices. We use the same method to model the reef effect of the offshore wind farm of Courseulles-sur-Mer. Indeed, as said earlier, wind turbines bring new hard substrate to the environment, which can benefit some species like mussels, for example. To model this, we first used a blank map as environmental drivers for all the ecospace groups. Then we introduced, using the same spatial temporal framework, new maps with the offshore wind farm in order to increase the habitat suitability for all the species predicted from a previous study, which is Raux et al. 2017, to benefit from the reef effect of the offshore wind farm. By doing so, we made the offshore wind farm more suitable for the species which are supposed to benefit from it. The reserve effect of the offshore wind farm, on the other hand, was modeled with the Ecospace MPA tool, and only 15% of the model was close to fishing, as to follow the promoter proposition to optimize fishing in the offshore wind farm. Finally, we built 3 fishing scenarios in order to test the potential effect of Brexit on fishing in the extended Bayesian. Fishing scenario included a first reference scenario without any changes to fishing, and 2 scenarios with the effect of Brexit that were built with fishing experts, with one scenario increasing overall fishing pressure and another one decreasing it. Currently, there is 2 tools to compute ENA indices with Ecopath with Ecosim. There is the network analysis tool with Ecospace, and there is the Ecosim network analysis tool with Ecosim. We used the newly built ENIR plugin of Ecospace built by Emma Arrhenius. And this plugin in Ecospace allows us to create score files for each time steps, for each cell and each time step of the Ecospace model. Then, using R and the ENR library, we computed ENA indices for each cell of the Ecospace model, and this allowed us to map ENA indices. Here you have the results for the reference scenario without any anthropogenic drivers, And we mapped the mean trophic level, the recycling index, the relative redundancy, and the system omnivory. We can clearly see a gradient from the coast to the offshore to the center of the English Channel, with higher value of indices near the coastline and lower value in the center of the English Channel. We then selected a selected group of ENA indices in order to do a k-mean clustering analysis in order to define multiple functional regions of the extended Bay of Seine. So we discriminated the ecosystem in 3 functional regions, including the coastal Bay of Seine region, the offshore Bay of Seine region, and the central English Channel region. And we later used those regions with a non-parametric effect size cliff delta test, to characterize ecosystem changes due to large-scale drivers like climate change and fishing. So what did we saw? We saw that with the effect of climate change in 2050, we had limited effects on ENA indices with only limited change per ENA indices, which are generally limited to 1 or 2 regions of the extended Bay of Seine ecospace model. So if you look at the relative redundancy of the flow in the model, we saw that only the most coastal region was impacted, and it slightly increased with the effect of climate change. For the mean trophic level, the more offshore region increased with the effect of climate change in 2050, but the more coastal one decreased with the effect of climate change. Overall, we saw a small increase in the ecosystem resilience with the effect of climate change in 2050. That wasn't the case at all for 2100, and we saw a very strong effect on all the region of the extended Bay of Seine and for all the ENA indices. The effect of climate change in 2100 was highly structuring, both spatially, as you can see here on the omnivory, with a strong increase of the omnivory in the more offshore region and a strong decrease of the omnivory in the more coastal regions. But it was also highly structuring on the ecosystem functioning itself, as I said, multiple ENA indices and thus multiple ecosystem properties. So large changes due to the effect of climate change. This is here visible on the strong to medium decrease of the relative redundancy inside of the offshore wind farm of the extended Bay of Seine. Not offshore wind farm, sorry, and the Ecospace model of the extended Bay of Seine, sorry. Overall, we saw a small to a large decrease of the ecosystem resilience, depending on the region of the extended Bay of Seine. For the effect of the offshore wind farm, we saw a very localized effect inside and around the offshore wind farm. The reef and reserve effect appeared to have a strong aggregating effect on multiple demersal fish groups, as well as a benefiting effect on multiple benthic groups. This resulted in a strong increase of the mean trophic level, omnivory, and relative redundancy inside of the offshore wind farm, which tend to indicate an increase of the resilience of the system inside the farm. Around the offshore wind farm, on the other hand, the aggregating effect of the demersal group inside the farm resulted in a slight decrease of the mean trophic level and of the system omnivory index, leading to a small decrease of the ecosystem resilience. Finally, our fishing scenarios didn't appear to have any significant effect on the ecosystem functioning, and we thus aggregated them for the cumulative effect assessment work. Now that we knew the effect of each of our driver, so mainly the offshore wind farm and climate change, we looked on each ENA indices. We computed the additive effect, which is the sum of the effect of each driver per ENA indices. We then compared the additive effect with the corresponding combined effect of climate change and of the offshore wind farm. If the additive effect and the combined effect were different on any ENA indices, then there was a cumulative response between the offshore wind farm and climate change. So for example, if the combined effect was greater than the additive effect on any ENA indices, then there was a synergistic relationship between climate change and the offshore wind farm for these ENA indices and thus for these ecosystem properties. Cumulative effect could be both positive, as it is visible here on the left, or negative, as it is visible here on the right, with a positive synergistic effect on the left and a negative synergistic effect on the right. However, if the combined effect of the offshore wind farm and of climate change was weaker than the additive effects on an ENA indices, then there was a dampened effect, and in this case, a positive dampened effect. Finally, if the additive effect and the combined effect were opposite on an ENA indices, then there was an antagonistic effect, and in this case, a positive antagonistic effect, because the combined effect of the offshore wind farm and of climate change was positive on the ENA indices. Because we used Ecospace, we did this for each cell of the Ecospace model, and we characterized the most significant cumulative effect. And we saw that for the same ENA indices, and in occurrence here, the omnivory index, cumulative effects could be both synergistic, antagonistic, and dampened, but at different positions in space. We saw that cumulative effects mainly appear inside of the offshore wind farm, as it is visible here on the recycling index. But some ENA indices displayed cumulative effect outside of the offshore wind farm in the spillover zone, like for example here on the omnivory, where you can see cumulative effect well outside of the park. Thus, depending on the ecosystem properties, cumulative effect could have a different spatial extent. Cumulative effect also varied between 2050 and 2100 for some ENA indices like the relative redundancy and the system omnivory. Therefore, the consequence of cumulative effect for the ecosystem resilience differed between 2050 and 2100. Indeed, in this table, the greener the box, the better the effect is for the ecosystem resilience. And we can clearly see an overall positive effect of the cumulative effect on the resilience in 2050 compared to 2100, where there is a mixed effect on the resilience due to the negative cumulative effect on the system relative redundancy and system omnivory. For some ENA indices, like the fin cycling index, so on the indices that is looking at the recycling of the network, we saw that cumulative effect didn't change between 2050 and 2100, only the intensity of cumulative effect did. If we look a little bit deeper, we can see that the positive synergistic effect on the recycling is the result of the interaction of the structuring effect of climate change with the benefiting effect of the offshore wind farm on the benthic activity. While alone, the offshore wind farm reduces slightly recycling, with the effect of climate change on the community of the extended Bay of Seine, both drivers interacted together toward an increase of the recycling and a positive synergistic effect. To conclude, we saw that cumulative effect could differ between ENA indices, and for the same cumulative scenario, cumulative effects were both variable in space and in time. Various cumulative effects were seen, and we saw that, surprisingly, in 2050, cumulative effects seem to increase the ecosystem functioning and resilience. In 2100, however, the strong effect of climate change on the ecosystem resulted in mixed cumulative effects with various degrees of negative effect on the ecosystem functioning and resilience. This work could benefit from a couple of improvements. First, we could test the effect of climate change with other large-scale drivers, because as we saw, our fishing scenarios weren't strong enough to be tested in the cumulative assessment work. So it could be interesting to do fishing scenarios with in order to test the cumulative effect of climate change and of fishing. We could also test our method in other ecosystems in order to compare the cumulative effect between different ecosystems and see what the structure of the network and what the functioning of the network do to the cumulative effects. Finally, we also want to increase the number of drivers, as ecosystems are impacted by a large number of drivers, and many scientific estimate that we should test cumulative effects with more than 2 to 3 anthropogenic drivers. It will also be interesting to integrate the model variability in our study and to do variability analysis to take into account the variability of the species distribution model outputs, because the species distribution model have a large scale of variability, and it would be very interesting to add this in our study to see how variable, for example, cumulative effects could be. So thank you for your attention, and thank you.
Thank you very much, Quentin. Maybe, I don't know if you want to stop sharing your screen.
Yes.
Or maybe, I don't know, maybe don't, because it, oops, too late.
Okay, no, I will.
You can maybe just start again, because I don't know if there's any questions. I'm not seeing any questions just yet. Kim, you have a question.
Yes.
Yes, thank you, Quentin, for a great talk. And I really liked your use of graphics in this presentation. My question is, what were the limitations of the habitat capacity model within Ecospace that made you choose to use species distribution models to determine the habitat suitability within your model area?
Instead of using like temperature map and habitat map?
Yeah, instead of using the habitat capacity model where you also include the environmental and other drivers in combination with response curves.
Yes, so I decided to use species distribution model because first we had a great set of species distribution model for a lot of species in the extended Bay of Seine, so data was available. And the thing is, I saw the paper of Marta Cole, which showed that using the habitat capacity model or the species distribution model seemed to have the same type of result. And in my opinion, the species distribution model, the particularity of the species distribution model is that they use various, first of all, they use various map of depth for at different maps of temperature at different depths for each type of species depending on their ecology. So we had very good species distribution model that took into consideration if the species was more benthic or more pelagic. So we have a lot of parameters. We took into consideration more parameters, I think, that I would have been able to take into consideration with the habitat capacity model. So because of the quality of our species distribution model, because of the amount of parameters that were taken into account, and because of the data availability, I decided to stick with the species distribution model. And the other interest, in my opinion, was in order to test the effect of climate change, because we had those different results. We have a validation method in our species distribution model, and we had all of this work that was done earlier. And both were for the multiple climate change scenario. I thought that it would be interesting to use a species distribution model in this case, because I know the community really wants to go forward with the link of species distribution and food web modeling. So it was a good opportunity to do so.
Great, excellent, thank you.
Thanks. And Cam? Oh, we can't hear you. So if you are speaking, we can't hear you. You've unmuted yourself, but we still can't hear you. I don't think it's the mask because. Hear me now? Yeah, there we go. Now we can hear you. Perfect.
Wrong microphone. Sorry. So you mentioned resilience. I'm sorry if you explained it, but it wasn't clear to me whether that was a quantitative term, and if so, how did you calculate it? Because I find there's a lot of confusion around this concept. So did you calculate it out of the model?
Sorry, I didn't hear.
So his question was on your I say index of resilience.
Okay.
Yeah.
So it was on the resilience. Okay. So basically, I first come from ENA from the ENA school, so because we had access to. So I'm gonna change to the good presentation slide, but. So for this work and earlier, the plugin was built by Emma Reynolds, which gave us the ability to get a score file for each cell of each time step of the model. And so basically those score files are flow matrix data. And then with this flow matrix data, we computed multiple ENA indices. Then to get access to the resilience, I basically look at all the theories based around those different ENA indices and how they are linked to the ecosystem resilience. And instead of using a single indices to see if the resilience was increasing or decreasing, I used it in cohesion. So I look at all the indices and I said, for example, if the relative redundancy, the fin cycling index, this value and this ENA increase, then I know then I suppose that the resilience of the system is increasing too. It's not, I don't quantify it. It's more of a qualitative approach and a trend on what would be the trend on the ecosystem resilience. But it's how I do it because I consider that for this type of work on the ENA indices, you should look at multiple ENA indices. And so that's how I did it. So basically, if all the ENA indices were indicating that the ecosystem resilience was increasing, my conclusion was, okay, the ecosystem resilience is increasing for this region or this case.
Something that can be quite easily tested from EWE. So it'd be interesting to see if your associations here that you've assumed are important, whether they actually translate to a more resilient system. You could do some simple tests to determine that.
Yeah, I think if I may, Camps was saying that you should be able to test it easily in Ecosystem, but I think my understanding is that there isn't a one term for resilience. That's a definition for resilience in the ENA indices.
That's exactly my point, Sheila. Is that people think coral reefs are resilient, but they're the opposite is true. So anyway, I just am always cautious when I hear that term, and particularly because EWE you can actually measure it based on the response. So, but yeah, I think there's a lot of confusion. I think the world would be a better place if people stopped using that term.
Quentin, did you want to answer to that?
Yes. I used the definition of ecological resilience from Holing et al. in 1996, but in this case, we know that there is multiple work on all of these ENA indices. They link them to the ecological resilience. It's not just my work. There is like a lot of people on it. And so the thing is, I just I looked at what everyone was saying about each of these ENA indices, and I only say that then for the ecosystem on its own, but I didn't try to look at if the model was more resilient or not based on the changes of the functioning, because it was more of a conclusion for the trend on the ecosystem. Sorry. But I didn't look at in the Ecospace model if this really changed into an increase of the resilience, because at the end of the day, the two systems, it's the modeling of the food web. So there is patterns of resilience that you could count for sorry, I can't find my word, but what I would say is that I used it based on the theory, and I just predicted potential changes and trend. But of course, I didn't test it on the Ecospace model itself and on the food web interaction model.
Thanks. So Natalia has another question in the chat, but before we go to her question, I'm going to ask my question because it's quite related. Can you go back to the method slide where you basically showed how you calculated the the next one, the one.
Okay, sorry.
That one, yes. So and this is just because I don't actually know how this is happening how the network analysis indices are actually being pulled through. So network analysis so you can get network analysis indices over time in like data time steps or something through EcoSim. And then how is it calculated in Ecospace?
So we use the ENR plugin from R in the library R, but basically there was a beta tool which is not available for the public, I think, which allowed us to compute a score file for each of the cell of each of the time step of the Ecospace model run. So when we run our model, it creates score file for each of our cell of our model for each time step. And then we introduce those score file in R, and we use the ENR plugin to compute ENA indices. But as you know, to compute these ENA indices, we needed the model to be stable. That's why in every of my simulation, I let the model stabilize themselves until the end. And then we also have an R routine for basically at the end, all the cells were pretty much all stable, but there were always zones that were unstable and where we wouldn't be able to compute ENA indices without a small modification. So we had a small routine that balance X, which helped us force the balance of the model in some case, doing relatively small changes to the flow matrix, but it was only for a limited amount of model. And when we used those and looked at the effect before and after this balancing, there was a continuity in the ENA values and no extreme values seemed to appear. So we had a good balance of those cells.
Thanks. I still haven't seen any questions and answers from the participants there, but I think the panelists are doing well. So Natalia asks, and I'm assuming she's on a train somewhere, so she's not going to speak her question. She's asked, she said she didn't know if she missed it, but how did you quantify the increases in biomasses of things like epifauna and benthos around the wind farms?
So basically, there was an earlier work that was done by Aurora Uxetal in 2017. She did her thesis on the potential ecosystemic impact of the offshore wind farm of Courseulles-sur-Mer, and she looked at different offshore wind farm in the North Sea and mainly in the North Sea because there is no offshore wind farm in the English Channel right now. And she looked at how much biomasses of certain groups would be introduced by the arrival of the new substrates. And then based on those changes, she ran an Ecopath model with an Ecosim model to run a model with the offshore wind farm and with the increased biomass of the different groups that would benefit from the effect of the offshore wind farm reef effect. So now in the Ecospace model, I used I saw how she forced her biomass in each of her model in her model with the reef effect, and I created new environmental driver maps, which how can I say that? Which simulated the exact same increase as she made on her model and as she estimated from the effect of the reef effect. So basically, based on her observation in other offshore wind farms in the North Sea, she estimated what would be the effect on the different groups, and then I translated that with the environmental drivers and the Ecospace model of the BFSM. I don't know if it answered the question.
She says thank you in the chat, so I'm assuming that explains. Okay. Okay, so I don't know if there's any other questions from the panelists or from the attendees. Kim?
Yeah, I had one more question about your species distribution models. I was wondering, for how many groups or species in your model did you have that information available, and how did
Oh, did we lose Kim?
Is it her?
Yes, I'm not hearing her anymore.
Yeah, so, but we can hear each other, so it's not us.
Okay.
Maybe you can start by answering how many species do you have?
Yes. So we run species distribution models for 72 of the species of 72 species, and I assume her question was about I don't exactly know, but we had so the 72 species were the main species of the extended Biocene, the one with the higher biomasses, But of course, and so represented the higher biomasses in each of the group of the Ecospace model. But of course, there were groups that were multi-specific, where there were multiple species in the group. So for those cases, we weighted the maps based on the percentage of the biomasses that each of the species represented in the Ecospace groups. And then we computed new map based on the weighted value for each of the species in those groups to create new environmental driver maps.
Okay, well, that's unfortunate because she's not there to hear your answer, but we can probably, if she comes back, we can revisit that. Do we have any other questions from any of the panelists? Oh, Kim, you're back.
Yeah, I got tossed out for some reason.
You must stop mid-sentence. So we answered your first part of your question. I think you did 72 species.
Okay.
You want to go with the rest of your question then?
Yeah, the rest of my question was simply how did you deal with potential groups or species that did not have a species distribution model?
Yes, so as I was saying, there were some groups that were composed of multiple species. And so for this case, because we did the 72 more abundant species of the extended Bay of Seine, we weighted based on the species that compose the group. We weighted the maps for each of the dominant species of the group, and we created a map based on the weighted maps of each of the species of the group as an environmental driver for those group here.
But I think the question was, what did you do with species for which you had no distribution map?
Oh, so if we had no distribution on, we use the value, you use the parameters from the previous model, which use the habitat map to drive species distribution, and basically based on only on their habitat, we use for the rest. Let's say like you prefer this habitat, we also had a map habitat, and so we waited for the rest with the habitat map. What were their preferences compared to the species distribution model?
Yeah, it sounded like you had a lot of species distribution models. Did you have 72? Is that what Sheila?
Yes. Yes, so there were a lot of species that were models, so that was the advantage. But of course, for some group like benthic groups, invertebrate benthic groups, we only had like the dominant species, but a lot of the lesser dominant species, we didn't have any species distribution models, so that's where we used as proxy our habitat map to do it. Inside with the species distribution model, and created new map with the weighted. With the weighted species distribution model of the dominant species and the habitat for the rest.
Great, thank you.
Okay, other questions? No. I had a question on the. Well, I have two questions, and both of them I'm not sure if there's an answer, but I'm going to ask them anyway. The first one is, it would be quite interesting to look at how the indices would change not in space. So if you looked at some of these indices like fin cycling index or any of those over time, compared to, say, the cumulative effects over space. I'm just wondering if there's a big difference between just looking at these indices over time versus looking at the spatial distribution of it. So that's my first question. And the reason I asked that is because you showed quite big differences between, say, onshore, offshore for some of these. And if that was the case, then if you didn't have time, then there might not be any difference. You might not see any difference. So that would be quite interesting to see if there's a correlation, or if it is at all the same. So maybe we'll start with that one.
Yes. So basically, because of the computation time needed for ENA indices, I didn't do a chronological analysis of the ENA indices. So we had a snapshots at different time periods. So for the current, for 2050, 2100, because computing the ENA indices using this method was not optimized yet, and so it took a lot of time. So I didn't take into time the fact of doing it ecologically. It could be done if you selected like a specific amount of time steps and created a map for each and try to, but I haven't done it, so I can't answer your question based on time. Now, what would be, so what was the second part of your question?
Well, okay, so if I understand correctly, you basically just use the end result of Ecospace to calculate the indices, right?
Yes.
But so even if you just ran Ecosim over time, ENA and Ecosim over time, you will get that outcome, and then you can still compare what you receive from that to say the cumulative effect that you might see, like if the index is increased by 10%, you know, cumulatively, but
yes.
In space, but only by 1% in if you just use the time. That's the kind of thing. So I don't think you need to do it. I don't think you need to do it spatially and space and wise. I don't think you need to, but I think it would be quite interesting to see.
Okay. The thing is, because it's quite small, because the offshore wind farm is quite small and the cumulative effects mainly appear inside of the offshore wind farm, I don't know if it would be that visible at the scale of the entire offshore wind farm. Maybe, but yeah, I see what you mean. Maybe for some indices where there is a more stronger effect, you could see it at the scale of the entire offshore wind farm. But one of the, but of course we didn't do it, so I can't talk about it.
Yeah, but I think it would be quite interesting because, and the reason why I'm asking that is because, you know, if you do say combined biomasses in a functional group, you will also have no trend. You might have no trend, even though inside the groups trends are going in opposite directions. So I'm just wondering if we don't look at the impact on these indices in space, but only in time, are we losing some information? That's kind of where I'm coming from. So that is more a question to myself, really. And I think the easy way to check that is just to run your Ecosim model for 100 years and look at what these indices are in 2050 and 2100 and see if it's quite similar, or if it's completely different, then, you know, we have to ask more fundamental questions about how it's calculated. So yeah, I don't know if there's an answer. As I said, I don't think there's an answer, but I just think it would be quite interesting to try and do that.
Yes.
My other question was about uncertainty, and you were saying that it would be interesting to look at sort of, you know, changes or differences, uncertainty in your input data. But I'm just wondering if it's how, well, firstly, I don't think it'll be easy, but also how different will it be if you only, you know, I mean, you basically would have to have, I don't know, 500 end-shot Ecospace models.
Yes. So basically, there was a work that did it, and there was like 25, I think, Ecospace model that we did in our project earlier. So there was 25 Ecospace model, and at first I was thinking of doing it too, because species distribution model can have very variable results depending on the circulation model, on the global circulation model, depending also on the algorithm, because we use multi-algorithm niche models. So there can be variability, and so I wanted to take into account this variability. I took it into account in a previous work which I did on the LIM model, on the linear inverse modeling. But in this one, and it's mainly due to problem with the methodology, because of the time it took to compute ENA indices. Doing it times 25 would be extremely long. And the thing is, because I'm also working on cumulative effects, it means that I have a lot of scenarios. I have a scenario for each driver. I have scenario combining the different driver, different forms. So it's quickly you run up with a 200 Ecospace model, and it would take years to compute. So it's a little bit complicated to do it that way. But I really want to optimize the ENA calculation and try to integrate it, because I think it's important when modeling the effect of climate change and with elements that bring so much uncertainty. And because I'm coming from the LIM model, I also like to take into account variability in the living, for example.
And then I see there's another question from Natalia asking about how you did your climate change scenario to 2001 to 2100. Was it driven by temperature and primary production, or how did you do that?
Well, because with the species distribution model, it was mainly with temperature and salinity. So I didn't force primary production. So the idea was, how would the effect of climate change have an impact on primary production in the extended Bay of Seine? And so I spoke with, initially I thought it would be the case, but I spoke with specialists in the extended Bay of Seine. And because it's a very shallow environment with a lot of turbidity seems to be the main parameter that is acting on photosynthesis. And so we talked a lot. We looked at what model we're predicting in the Bay of Seine, and in many cases there were no uniform information about how would the primary production evolve with climate change in the extended Bay of Seine. So I decided to don't touch it for those models, because we didn't have enough information, and the local expert was saying that it was more linked to other parameters. So we didn't play with the primary production, but it could be interesting. But I would really like to be able to do it. So maybe it's something that will happen later.
Mm-hmm. All right, thank you very much. I'm seeing any questions coming through the Q&A. I don't know if any of the other panelists have any more questions to Quentin, or any other Ecopath questions. If you have them that we can answer, then now is your time. I think we have 10 minutes left, so we're happy to ask any other questions, answer any other questions if people have them. Otherwise, yeah, we can go have some lunch, breakfast, dinner, whatever, whatever is your comfort. Wine for Lee, I think. So I'm not sure if there's any other questions. I think it doesn't look like it. So I think a lot of people in the chat have said that it's been a great presentation, Lee. So I think it's been quite interesting. It's really been interesting for me. So if there's no other questions, then I think that would be it. We can end the webinar, except if somebody else has something to say. Santiago, Cam, no, Lee, no. All right. In that case, thank you very much.
Thank you, Sheila, for inviting me.
And just for those of you who are around, we are, as far as I know, we do not have a speaker for January. So as Lee, am I wrong? Do we have somebody? I don't think so. So if anybody else wants to give a presentation in January, then speak now. Well, speak later. You can email us. But thank you very much again, Quentin. That was great, and good luck for your defense on next week.
Thank you very much.
Thank you.
Right.
Thank you.
Thank you.
Thanks. Bye, guys.
Bye.
Bye-bye. All right. Okay. In that case.
I don't know if I needed to stay or to talk about it.
No, that's okay. I think we're still on YouTube, so I'm going to end it and then.
Okay.
All right.